Okay, welcome to my note. My name is Ariella Rosenbaum. I teach a computer science course here. I actually live in Columbus, Ohio, and I teach remotely, but I'm here for my vacation and to be here with you. So we're going to talk about Einstein's relativity today, and I'm going to try to make it simple. I hope it goes well. There is a sheet that has some pictures on it that you can pass around. So we're going to start with something very simple. When I traveled from Columbus, Ohio to East Brunswick last week, I traveled around 530 miles. It took me a little less than 8 hours. So in order to calculate my average speed or how quickly I traveled, it comes out to around 66 miles per hour, which is pretty good time. And I can measure that distance in time with a ruler myself. You could have measured it with some sort of ruler device and measured how far and how much time using a stopwatch I traveled. This concept of speed has been around for a long time. And what we're going to do is we're going to take that idea and bring it into the 1600s, the 17th century, and then today. So we're going to start with Galileo. He was an astronomer in the 1600s, and he was famous for a few things. One of them, you can see his telescope here. He made a very good telescope and was an astronomer. And one of the things that he's most famous for is this image, which is actually Copernicus's image from earlier, the idea that the sun is actually in the center of the universe. He supported that theory using his telescope. That's the sun, the sol. This is the Earth with the moon traveling in a circle. Here we have the stars and the other planets. And he got in big trouble for that with the church, was on house arrest, and eventually died while on house arrest. Another thing he's famous for, which we talk about in our physics classes here at Maya Note, we talk about objects falling, and he was the one who probably didn't actually perform this experiment, but the story is that he dropped things off the Tower of Pisa and measured how quickly objects fall. So those are things that he's famous for. But another thing that he is famous for is talking about relativity. So the first question I'm going to ask you is, how fast is the car moving? Now, it's hard to see, but if you look at the, I have one here. It's a little bit lighter. If you look at the speedometer, it reads at about 30 miles per hour. So if I asked you how fast is the car moving, most people would say it's moving at 30 miles per hour. But when we talk about speed, what Galileo said is that speed actually depends on what your perspective is, what we call frame of reference is. So if I'm watching the car go down the highway and I measure how fast it's going, I'm going to get 30 miles per hour. I'm going to see that he goes 30 miles in an hour. But if I measure the speed of the car relative to the driver, and the driver stays in his seat the whole time, the speed of the car is actually moving. The car is not moving relative to the person in the car. And if I have a passenger sitting next, we can have a whole conversation, and we're not moving relative to each other. So relative to the ground, I'm moving at 30 miles per hour. But relative to the person walking next to me, we're not moving relative to each other. We're staying next to each other the whole time. You can also see this. I chose this picture because if you're the driver, sometimes I get this sensation when I drive. Am I moving forward, or is everything like the trees moving backward? So like we always say, oh, the car moves forward. It's not the trees that are passing by us in the backward direction. But from a physics perspective, it actually doesn't matter how we look at speed, as long as you just say what you're measuring it relative to. Now, normally in the world, if you say something is traveling 600 miles per hour, right, you're doing it relative to the ground. That's what we usually call our at rest. But what your speed is actually is irrelevant, as long as you just say what it's relative to. Another example I like to give is when you're driving on the highway and there's a car, hopefully in the opposite side of the highway, going at the same speed backwards. I could say that I'm not moving. I'm moving at 30 miles per hour, but I could say I'm not moving, but that car is going at 60 miles per hour, like really fast that way. So that's just his speed relative to me could be different with moving objects. So he actually quantified that mathematically. It's called a Galilean transformation. Transformation just means some sort of mathematical way of manipulating something in different situations. So the example that I brought is we have a train, a person walking on that train, and then a person watching the train moving, and the person walking on the train. So the train is moving relative, that T and G means the speed of the train relative to the ground is 9 miles per hour, 9 meters per second. The person on the train, who's walking on the train, is the person walking on the train is walking at 2 meters per second. But the person on the ground watching this is going to see those velocities or those speeds added together for a total of 11 meters per second. And I remember experiencing this, like if you're in an airport and you're watching somebody walk on a moving sidewalk, and they look like they're running, but they're not. So they have their speed of whatever they're walking at, plus the speed of the moving sidewalk. So me watching this happen, looks like they're going really fast. And the same can be true if they're walking backwards, right? You always have little kids trying to play around because they're bored in the airport. So they're trying to walk backwards on the moving sidewalk and see if they can keep up pace or get to the other side. So they have to walk really fast to negate those effects. Another example of this is if you throw an object off of a moving object. So here we have someone throwing a snowball. The little girl is throwing a snowball off of her sled that's being pulled forward. So the sled and the girl are moving forward at 1 meter per second. She throws the snowball forward at 1.5 meters per second. So me, or somebody, watching this happen will get hit by a snowball moving at 2.5 meters per second. They get added together. And if she throws it backwards off the back, you would subtract those values, and in this case it ends up going backwards at 0.5 meters per second. So the speeds can be added or subtracted based on how you're viewing it, where you are, and if you're moving forwards or moving backwards. And that's all called a Galilean transformation, where we just add and subtract velocities moving in straight lines. Another aspect that Galileo came up with on relativity has to do with what your perspective is and what do you see the motion as being. So an example of this, and this is an example of an experiment that Galileo did on a ship. I don't think it was with a pair of binoculars, but with objects. He had someone go to the top of the mast and drop an object while the ship is moving forward at some constant speed. And from the perspective of everyone on the ship, it was a straight line down motion hit right below the mast. But if I'm on the side, if I'm on the coast watching this happen, everything on the ship, including the dropped object and the person and the mast and everything on the ship, is moving forward with a certain speed. And that got added to the speed of everything, including this object. So what I see, if I tracked it, I would see a curved motion. This idea that something that looks straight for me can look curved for somebody else, or not look at motion at all. So another example would be, what if you are the thing that's being dropped? So my perspective of myself would be I'm not moving. Maybe everything else is moving. Maybe the ship is moving up towards me. So this idea that the actual path could be very different is also part of Galileo's idea of relative motion. It's relative to your perspective and where you are. Are you on the ship or are you not on the ship? The third idea that Galileo kind of brought out with his idea of relativity, which relates to Newton's laws of motion that we're not going to get into, is called Galileo's ship. This is actually a thought experiment. It was kind of hard for him to do, but I'll give you a modern day example. His idea is that if you have a person with all sorts of objects in the hold bottom of a ship, and he doesn't have any way of seeing out or knowing what's going out on below, if he's on a steady water, moving at a constant speed, and he has no way of knowing what's going on in the outside world, he would have no way of knowing if he's at rest or if he's actually moving forward, but at a constant speed. So that's what they show here. If the carriage is standing still, all the laws of physics do what they're supposed to do, and it's exactly the same if you're moving forward uniformly. Here means constant speed, straight motion, no turns. But if you start accelerating, meaning going faster, going slower, changing direction, all of a sudden things don't go in straight lines and start moving in weird ways. A modern example of this would be when you go on the plane and you fall asleep and then you wake up and you're like, wait, did we land? Like, are we still moving? If there's no turbulence and the plane's going at constant speed, it's really hard to tell, and you kind of get disoriented for a second. But if the plane starts, descending, or there's a lot of turbulence, then you'll know, oh yeah, I'm still on the plane and we're still going towards our destination. So the idea that the laws of physics are the same if you're standing still as when you're moving at a constant velocity is the reason why you can get up during a plane ride when there's no turbulence, and they can pour you a drink and it's not spilling all over the place, usually. And the fact that when you get disoriented for that minute, that's normal. Like, there's no way of knowing if you're moving unless you look out and maybe see the clouds going by, but maybe that's a cloud machine. Like, how do you know? So all of that is Galileo's idea of relativity. We teach it in a regular physics class. It's part of motion. It fits in all the laws of motion that Newton came up and other things that we discuss. But the problem comes in when we get to the 1800s, and in this area of physics, what's happening is all the areas of physics initially are separate. We have people looking at motion, people looking at waves, people looking at heat, people looking at electricity, magnetism, like they're all separate fields. And you have people who kind of dabble in both, but it's like separate notebooks, separate courses. There's no relationship between all those fields. And James Clerk Maxwell, this guy over here, was working on electricity, magnetism, some waves, and he starts finding some bridges, some connections between electricity and magnetism, and he comes up with this new theory of electromagnetism, putting them together. And part of that is he was able to incorporate the idea of light and radiation into his theory of electromagnetism, that they're related. I made slides to go into that and then threw them at the bottom because I don't have time. But it's very interesting, his work and how it relates to light. So here was the problem that came up. At this time, people already knew that the speed of light, how fast light travels, is very fast. So in a vacuum, there's nothing in its way. Light can travel at approximately 300 million meters per second, or in miles per hour, 670,000 miles per hour. Very fast. That would have been nice for my trip from Columbus. The problem is that when James was doing his work, when Maxwell was doing his work on electricity and magnetism, in his work on electricity and magnetism, his work, the mathematical derivations he was coming out with, said that the speed of light should be constant no matter what frame of reference. If you're moving or not moving, you shouldn't be able to add or subtract to the speed of light. So if you have, let's say, the headlight on the front of the train, guiding the way forward, so Galileo says whatever the speed of the train is gets added to the speed of the light, same way with the person walking on the sidewalk. That should get added, so the speed of the light, if I'm watching this happening, I should see the beam of light traveling faster, okay, than if it was just standing still. And the same other way, if I have the light at the caboose shining backwards, it should be able to be less, according to Galileo. But Maxwell's formulas wasn't showing that. So there was an experiment that was done. It was to prove a few other things, but one of the things that came out of this experiment is called the Michelson and Morley experiment. It was done in America in the 1800s, late 1800s. They used a whole bunch of mirrors and lasers, and what they used for speed, because the speed of light's really fast, so you got to add something big to that to maybe measure the difference. So they used the speed of the Earth. The speed of the Earth. So they set up their mirrors so that in one direction, the Earth was going in the same direction as their laser, so it should get added. And then they turned the laser around, actually turned the whole machine around. This machine was on, I don't know if you can see on the bottom, it was on like ball bearings and like oiled ball bearings. They could like turn this whole big machine, like this is a big square, like around. And they were trying to see if the speed of light, if there was a difference between when it was going with the Earth and should it get added, or away from the Earth and should it get subtracted. And their results were that it didn't get added and it didn't get subtracted. So Maxwell said, speed of light should be constant, I can't add and subtract to it. This experiment confirmed that, but Galileo says it should be able to add and subtract. So the question is, who is right? And how do these two theories fit together? Yes?
Wouldn't gravity have an effect on the speed and light not be within gravity?
So we're going to talk about Einstein's theory, and the theory we're going to talk about today is his special theory of relativity, which does does not include gravity. And his theory of general relativity, which came 10 years later, which I do not have time to talk about today, that's where he pulls in all the gravity and explains it together.
Before Einstein, I don't know anything about Einstein, but even at this time, they already knew about gravity by Maxwell's time, right?
Right, so they were not unifying that part of the theory yet. Like he was putting together electricity and magnetism. Gravity was a totally separate,
He didn't think
unrelated.
gravity had the fact that light wasn't within gravity. He didn't think that would have an effect.
I don't know. But they definitely weren't trying to put them together yet. Einstein did, and that's part of the beauty of his second theory, which is the theory of general relativity, is putting together even more fields of physics and putting it together as much as he can. Okay, so now we get to Albert Einstein. So he comes into this scenario where we have Galileo saying speeds can add and subtract, and we experience that in our everyday lives, but when it comes to light, Maxwell says that shouldn't happen, and we have experiments that it's unclear if he knew that experiment had gone on. He wasn't really part of the physics world. He was a German patent clerk. He took some physics and math classes, but a lot of this was like going on in his mind while he was doing mindless work for the government. So it's unclear if he knew about the experiment that happened here. It's unclear from his papers and his work if he knew about this experiment, but he definitely knew about the work of James Maxwell. He definitely knew about the work of Galileo. So in 1905, this is called his Annus Mirabilis, which means the miracle year. This is the year where he published 3 papers and 1 addendum that changed physics forever, and not just in one area, in many areas. So his first paper he wrote was a paper on Brownian motion, which gave a very, like one of the most convincing proofs on the existence of atoms. Even though at this point people had accepted that they were there, he kind of gave a much better mathematical and physical proof for them. The photoelectric effect is related to a completely unrelated field to this, which is called quantum mechanics, which is for another time. Special relativity, which is what we're going to talk about today. And this famous equation was actually a footnote addendum. After he wrote this paper, he's like, I wonder how this relates to energy and mass, and he came up with this formula. So that was kind of like an afterthought, but it became one of the most famous equations, I think, in history. We're going to be focusing on this. This word here, can you pronounce it? Yeah, that. Okay, so that's German for thought experiment. Einstein did not have a lab. He did not do experiments. He did a lot of thought. And he thought about scenarios. How would the physical aspects of our world apply to either extreme examples or examples that you couldn't actually do, but we could think about what their effects would be. So a lot of what we're going to talk about are his thought experiments and other people's thought experiments. So the first part of his special theory of relativity, by the way, special relativity, the only thing special about it is that it only applies to certain cases. So if anything, I wouldn't call it specific theory of relativity. The specific theory related to this specific case, which we're going to talk about, his general theory, which I'll mention later, kind of broadens that to more aspects of the world. Okay, so his first idea is the relativity postulate. The relativity postulate says that, similar to what we said before, if you're in that box that's moving, and it's moving at a constant velocity, a constant speed, you don't have any windows, there's no way for you in any way, shape, or form to figure out if you're moving. Now, the part that he added, and he made it more specific, is the idea that there is no absolute at-rest reference frame. So before that, people would say, well, there's something somewhere that's the at-rest place, and everything is moving relative to that. So the Earth moves relative to that, and the sun moves relative to that at-rest space, wherever that is or whatever that is. So people thought there was somewhere that's not moving, and everything's moving relative to that thing and moving relative to each other. So what he said is that there actually is no place or space that's at rest. However, we can measure speed by measuring relative to other things, and we can do it to lots of other things depending on how they're moving. So he kind of made that not just, you can measure things relative to each other, like Galileo said. He said there's no place or space, that this is the thing that's not moving and everything else is moving. He said the way we measure speed is by measuring things relative to other things, and that's the way it is. That idea is, sorry, this is new for me. That idea was revolutionary on itself. It's kind of hard to wrap your head around. Like, there's no place that's not moving. We just have things not moving relative to other things. But that's what he said. We're going to focus more on his second postulate. His second idea is that light travels the same speed no matter how it's moving. So if I have the train with the light in the front and the train's moving forward, Galileo said you can add. Einstein said no, speed of light will always be that speed, 300 million meters per second, whether I'm on the train, off the train, train's moving forward, train's moving backward, there's no adding and subtracting to the speed of light. And that's going to have some big consequences.
Why did he say that? Because it's not a physical particle, because of his waves,
So he said that because otherwise, if you can go faster than the speed of light, the problem with that. Okay. See, I skipped this. I skipped discussing what light was. It's later. I can show you. Sorry, skipping ahead. I cut out a lot. Hold on. So the problem is that when you look at the speed of waves, most waves travel through materials like solid, liquid, gas, but they travel faster when they're moving in solid things. So the problem is light travels faster when it's not in the solid thing, and it actually travels the fastest when it's in a vacuum. So you can't go faster than that. You can't go faster than, if it travels the fastest in nothing, you can't go faster. There's nothing beyond nothing. Does that make sense? A little bit? I know none of this makes sense. But that's the idea that for regular waves like sound waves, they travel slowest in a vacuum. They don't travel in a vacuum. They travel really slow in the air. But like in like earthquakes, waves in the ground travel at 5,000 meters per second, as opposed to sound waves in the air only travel about 300 meters per second. So waves that travel through material travel fastest through solids, and the thicker the solid is and the more elastic it is, the faster it travels. But because light travels the fastest in nothing, you can't travel faster than nothing. So light travels the slowest in solids.
So if you put a train in a vacuum,
What about the train?
and put do the train measurement with the train being in a vacuum,
Then what would happen?
I'm saying.
So the light would travel at the speed of light. You can't add to that the speed of the train. So it won't be traveling at 300 million meters per second plus the 500 meters per second of the train. So you can't add to that because you can't travel faster than the fastest it travels in nothing.
It's like the infinite.
Right, like you can't right, exactly. So this idea of that there's this universal speed limit, that's what we call it. The universal speed limit, 186,000, that's supposed to be miles per second. So nothing can travel faster than light. So he's the one who said that, and therefore it becomes a constant. Like, this is the value, you can't go faster than that value. Which fits with what Maxwell said was electricity and magnetism, it fits with that value. Now, because that's the universal speed limit, and it's the same, we can't catch up to that. So if we try to make something faster and faster, it can't go faster than that. That's the speed limit, because you can't go faster than the speed of light. Okay, so how do we add speeds of objects when we're dealing with this problem? So this is the only math on the whole thing. This is Galileo's formula for adding speeds. So this is how he would add speeds. He didn't deal with very fast things, but if I shoot an arrow from the ground at 200 kilometers per hour, and a different arrow with 100 kilometers per hour of the train and the 200 kilometers per hour of the arrow, this arrow on the top should go at 300 kilometers per hour according to this formula. 100 plus 200 is 300. You add them together, it's going to be faster. That's why like javelin throwers run and then throw, because they get their running speed plus their throwing speed. Okay, Einstein's formula looks a little different. He came up with this math, but somebody had already come up with this math before. A mathematician had done some work kind of figuring out different transformations. So this is actually not known as the Einstein transformation. It's known as the Lorentz transformation, after the guy who did the math first. But he did the math but didn't realize the consequences of what that meant. So this is the math for that. And the question is, what happens when I add speeds but I have a limit? Because in this formula, I could add speeds and get faster than the speed of light, but I'm not allowed. Einstein said no. So here's an example of that. Here is a rocket traveling at 50% the speed of light. C stands for the speed of light, so quite fast, 150 million meters per second. And that rocket shoots a canister towards a person standing on Earth, and that canister has a speed of 75% the speed of light when it's shot off of the spaceship. So again, if you're running and throwing, you get both speeds, presumably. So according to Galileo, when you add those two speeds, you get 125% the speed of light. For Galileo, that's not a problem. You can go. There's no speed limit. You can go faster than the speed of light. So Einstein said no, there's a universal speed limit for the reasons we talked about, and for many reasons that I'm not going to, and I also probably don't fully understand. But there's a universal speed limit, but his formula, the way it works, it will automatically limit you at c. So no matter what values you put in, it will work out to be c. This is what it looks like when you plug in those formulas, and when you actually do the math, it comes out to about 91% the speed of light. So it should be 125% according to Galileo, which is very fast. Einstein says no, the person watching this canister come to them will not see that object move at 125% of the speed of light. They'll only see moving at about 91. Now, that's true for these really big speeds, but what about these arrows? Do these arrows still add up to 300 according to Galileo? So Einstein said no. Einstein said you still have to use his formula, and then when you add 100 and 200 in this formula, you should get something less than 300. Now, in our everyday life, that difference is going to be 299.99999. So in our everyday life, are we going to care about that tiny portion of a percent that is lost when you add speeds according to Einstein? No, which is why in our physics class, this formula V1 plus V2 works perfectly fine. But if you start dealing with things moving very fast, which in Einstein's era they are, okay, satellites are going to start happening in the 1960s. We're going to start discovering particles that move very quickly through space. So that information is going to become very relevant. Okay, so what are the consequences other than this speed adding that doesn't add exactly? It adds but gets smaller. Yes?
Can I ask a question?
Sure.
I'm not getting at the slower speeds. The fact that you can't go more than the speed of light, why should that have an effect that at the lower speeds you can't use Galileo? It would need
Yes.
Einstein's equation.
So Einstein's equation, when we find equations in physics, there should be an equation that works for all scenarios, but certain parts of the equation end up getting dropped out because their significance becomes very low. So in this example, do you see this part V1, V2 over C squared? So when V1 and V2, those two speeds are very small, so you get that these two values, which is the same as that, see how V1 plus V1 up here, V1 plus V2 is the same as V1 plus V2 up here. So this top is the same as this. When you do a very small number divided by c squared is speed of light times speed of light, it's huge. So this number becomes 1.000000000 something, and anything divided by 1 is essentially the number it is. So it does make a difference, but it's so small that we can and we do ignore it in our everyday lives.
I mean, why does it make a difference? Why does
So
the
at
speed
low
of
speeds
light
it won't. It won't make a difference. But
you're saying we don't notice it, but essentially there is you're saying that.
Yes, I'll show you an experiment where they do an experiment at speeds that we've traveled at that shows the difference. But again, it shows the difference in an experiment, but you're not going to be looking at your watch and caring. But he said it applies to any speed. So I'll show you, after we do time dilation, there's an experiment that I'm going to talk about where it happens on an airplane. So these are, if anyone's been on an airplane, you've experienced this. I'll tell you that you're a little younger than you were before. Yay. Go on planes more often. Okay, so what we're now going to talk about is the consequences other than speed of what does this mean for relativity. What? Okay, so the first one is called time dilation. Dilation, like if you double bread, means to get bigger. So what does that mean? So again, Einstein came up with these. Say the word again, Ari.
The Dawkins theory.
That. Okay, so these thought experiments. That's my husband, by the way. Say hi. Okay, so Einstein did a lot of thought experiments. So he was thinking about scenarios like where would this come into play, this idea that there's a speed limit of light and the idea that the speed of light is the same and doesn't get added if you're in different time frames, different reference frames. So this is his light clock. He imagined this scenario where I have a mirror and a second mirror, and I have a beam of light, like a little pulse, traveling back and forth. So when it hits the second mirror here, that would be a tick, and down would be a tock. So tick, tock, tick, tock, tick, tock. It's a clock using a beam of light between two mirrors. Okay, so what if we take that mirror and we're in a reference frame where we're not moving? So I'm just watching it right here, up and down, up and down. The beam of light travels at 300 million meters per second. So it travels, hold on, up 300 million meters per second, tick, 300 million meters per second, tock, and so forth. And it has to travel up for the tick, this distance, down for the tock, that distance. Okay, but what if this clock's on a train? And I'm on the side, watching the train go by, with this clock doing the tick and the tock. But when I watch it, remember back here, if I'm on the perspective, it looks like it's just going up and down. If I'm watching it go across, I see a different motion and a different distance. Same thing here. If I'm watching this clock, sorry, it's got to get to the beginning again. So if I'm here, it now has to travel up this length, because it's moving across on the train. Tick. Takes much longer to get to the top. And that's for this reason. We said the speed of light is constant no matter where you are. It doesn't get added to the speed of the train. So the speed of the light travels here, the same speed here, but which is the bigger distance? This one or this one? Which is the bigger length? Just going up along this straight part or this longer line? I just gave the answer. This one's much longer. It's much longer than this distance. Sorry. So the light has to travel longer distance because it's moving, but it only can travel at the same speed. So it takes more time to hit the top to make that first tick, and then again more time to hit that first tock. But that's only if you're where? If you're watching the clock, and where's the clock and where are you? I'm here, the clock is there, and I see that. So when I'm watching the clock and the clock is zooming past me, I hear a tick, and then I wait, and I'm like, wait a minute, mine already tocked. They didn't tock yet. But if I'm on the train and I'm watching the clock, I don't see this across motion. Same with the guy on the mast dropping the object, go straight down. If I'm on the train, I see a regular tick, tock, tick, tock. It's only the person watching on the side, watching this train go by, it's like, they don't match. And that's the idea of time dilation, that it takes more time, and time seems to go slower when the clock is moving. Yes?
This is all assuming that that train is moving incredibly fast.
So you're not going to notice it unless it's moving fast. Like this is moving, I think this animation that someone made is moving at 50% the speed of light. No, it's moving at 87% the speed of light, which accounts for 50% time dilation. So moving it, but like we don't have trains going that fast. Okay, so this is time dilation. This was, there was an experiment that was done using stars earlier called the de Sitter experiment, if you want to look that one up. But a more concrete example, other than like things in the stars. So in 1971, Haefel and Keating did an experiment where they took 4 cesium clocks. Cesium clocks are accurate to several decimal places more than any clock that we have. So it's a very, very accurate clock. They set them up in the lab, made sure they were synchronized, did all these sorts of tests, and make sure that they were in sync with each other. And then they packed 2 of them up, stuck them on a plane, and traveled around the world one way and around the world the other way, and then compared the clocks. And they found a difference in the clocks. The clocks that were on the plane were slower, not as much time had passed according to the clocks on the ground, so the clocks were off. And they were off according to the formula. Now, I only gave you the formula for speed. There's another formula for time dilation, which is more complicated. But using this formula, we can derive a formula for how much time it takes to travel. And they found that their experiment very much agreed with Einstein's prediction that when clocks are moving, they tick and tock much slower.
Does it matter which direction?
No, because remember, it doesn't matter which way you're adding
No,
speed.
I'm just curious because,
Yeah. Now, here's an interesting problem. Remember we said that the person on the train, if it's moving at constant speed, they don't know that they're moving. So they say their clock is regular, tick-tock, tick-tock, tick-tock. But the person out here says, no, your clock is slow. Now the person on the train is moving by, they're watching their clock, and they're saying, no, their clock is slow. Because remember, if I'm in the car, I can pretend that I'm not moving and the Earth is passing by me. So actually, the only way you can tell which is the slower clock is when the object that was moving, let's say the train, stops. And then when you compare them in the same time frame, the same reference frame, that's where you'll see the difference. So while they're on the plane, if they could see the clock going on in the lab, they would say that one's going slow. But then when you put them in the same place, in the same reference frame, neither one is moving, that's where you'll see the difference of the clocks. Yes?
So if you cut off the plane,
Cut
could
off
you
the plane.
what?
Get off the
When you
Get off the plane, your
could
clock.
your watch actually be 5
So
minutes slower
our
than everyone else's?
you'd have to go
I
very
just
fast.
don't understand.
You'd have a difference. To have a difference of 5 minutes, you'd have to move much faster than we can get trains or planes to
Oh,
move.
okay. So it's not much of a difference.
Our clocks we're not going to notice, but if you had a cesium clock,
Okay.
besides the fact that it's radioactive, so you don't want a cesium clock, but if you had a cesium clock, you would see it. So they saw that difference. So again, like in our everyday lives, that's why this stuff was so unintuitive, and people thought he was crazy. They're like, you don't experience, that's not the way the world works. And they're right. We don't teach any of this in our physics class in my note, and it's not because it's not a good school. It's because when we first teach physics, you teach the stuff that it's not always intuitive, but the stuff that we experience in our everyday life.
Right. That's relevant.
You probably don't experience this in your everyday life. You're not moving that fast. Okay, so this is a famous thought experiment related to time dilation called the twin paradox. So the twin paradox is a story, a fake story, a thought story of two twins. One becomes an astronaut and says, I'm going on a trip, traveling far out into the universe, very, very fast. 50% the speed of light. I'm on the best spaceship that does not exist yet, and I'll be back later. Goes on the trip, comes back. Remember, when you're moving very fast in that spaceship, time goes slower. So according to Einstein's special theory of relativity, when the twin comes back and gets off, the twin who was left on Earth, time was much faster. They aged faster. So we see there's been more time. And coming back, again, depending on how fast the speed of the spaceship actually was, time will have gone slower for that person on the spaceship, moving quickly. We don't have spaceships moving fast enough and people descend on them that are twins, so we haven't done this experiment. But scientists have done an experiment where they bring, I think it was bacteria, like fast reproducing bacteria into outer space, into space stations, and they measure how quickly do they reproduce on Earth versus on the spaceship. And accounting for other things, they do reproduce less. So time for them is slower. And you can actually look up online the different astronauts. You can look online lists like this astronaut, how much time they've spent in space, how fast they were moving on the different things they were moving, and therefore like what their age on Earth is versus their younger age. And again, at the speeds we're moving at, the difference is a couple seconds. It's not a big difference. But again, the faster things are moving, and for particles that we do experiments on that do move very fast, we actually do notice a difference. Okay, another consequence of special relativity that's connected to time dilation is what's called length contraction. Length contraction means to get smaller. And what that means is that if I'm watching this, in this case it's a bicycle, but if I'm watching the train go by and the clock go by, the distance, the length of that object in the direction that it's moving actually contracts, gets smaller. So if I'm measuring that train that's really 25 meters long and it's passing really fast, if I'm measuring it, I'm only going to get 24 or even less. These pictures, this picture and then later this picture, is from a book called Mr. Tompkins in Wonderland. Now it's called Mr. Tompkins in paperback. It was a series of articles written in the 1900s by a famous mathematician called George Gamow, and he basically wrote these fantastical stories about this banker called Mr. Tompkins, and he would go to a physics lecture, promptly fall asleep, which I see none of you have done, so very good, So he would probably fall asleep, and he would be transported to this land where there the constants were values that actually we can experience. So like you said, like we don't experience in everyday life. That's because the speed of light is really fast, 300 million meters per second. I think the fastest we've had a land car go is about 1,000 miles per hour on these specialized cars with like jets on the back. We're not moving at speeds anywhere near the speed of light. So again, we don't notice it. But in where Mr. Tompkins goes, there the speed of light is set at 10 kilometers per hour, which is much more reachable. So what happens is this is Mr. Tompkins, and he's watching this guy on the bicycle go by, and as the guy goes by, he's getting skinnier and skinnier as he gets faster. So this is called length contraction. It's, again, the same way that time took longer. When I try to measure a moving object, the moving object actually, I will measure it as having a smaller distance than if it were standing still. What's interesting about that is, remember, if I'm the person on the bicycle, right, it could be that I'm not moving and the world is moving around me. So in that case, if I'm the bicyclist watching around, it would look like the people in the streets and all those things contracted and got shorter. So this is another consequence of special theory of relativity. They've also done experiments on this using particles that they have travel, and they see how long they last, what their distance is, and that distance correlated with the value that Einstein predicted. He predicted a certain value that it should be shortened by, and he got those values. Good. This is just a summary. I actually gave you this picture of those two ideas, that if an object is moving at a speed that's fast enough, the object that's moving, the clock will be slower, and the ruler will be shorter. But if I am measuring on a stationary observer, you would have a longer, or the actual ruler size, and a faster clock. This actually does become relevant. Today's day and age, we use satellites, GPS, radar. All of that is using beams of light being sent around. So they do have to take into account differences in time, differences in length when they make their calculation. If they're using radar to determine, where an object is, and they're about to, send a bomb or something, they want to make sure they're not off. And depending on where that satellite is, it can make a difference. When they sent out the rover, the new Mars expedition that they just sent out, they have to take these into account because it's far away, it's moving fast, and they have to make sure that their timing and their measurements are accurate to what we want them to be. But again, in your everyday life, if you experience this, go to your doctor. Okay. Another effect of this is whether or not two events are simultaneous.
Session number 1 should wrap up in about a minute, and we will still start session number 2 at 11:45.
Perfect.
Thank you.
Okay. So simultaneous events is whether or not two events are simultaneous. Here we have an observer from the ground, two lightning strikes happening in his perspective at the same time. The light comes to him, they both hit at the same time. But if you're in a moving car, okay, that's moving appreciably at some speed of light, in this case they have 4/5 the speed of light, it would seem to you that this one came before this one. So the question is, are the lightning strikes simultaneous? Are they not? Depends on your perspective. It's relative to whether or not you are moving or not. In this case, he says, yes, they happen at the same time. And this person says, no, this one happened first. It also works if the light beam is happening. There's a thought experiment where you have a light beam that's being shown across to both the front and the back of the train. And the person on the train will say that they reached him, like one coming forward, one coming backwards to the middle. He'll say the beam of light came at the same time. But the people on the ground will say, no, this one on this side actually came to him first, and this one came later. So whether or not the events are simultaneous depends on this. And again, in our everyday life, it's not going to matter. Okay. That was as simple of special relativity as I thought I can manage. I hope it was okay. So that was all 1905. Again, the special here just means that we're moving at a constant speed. He's unifying relativity and relative motion of Galileo with electricity and magnetism that Maxwell came up with the speed of light. 10 years later, so during those 10 years, he became a physics professor, got all sorts of awards. People kind of thought he was over. Scientists usually come up with 1, maybe 2. He already came up with 3, 4 if you count the addendum breakthroughs. They thought he was done. He'll be a physics professor, he's famous, he'll win a Nobel Prize, great. And then 10 years later, he surprised the world by coming up with his general theory of relativity, where he applied that to objects that are moving faster, moving slower. So he expanded it to include more scenarios, and he unified it with gravity. So he brought gravity into the picture. That's the famous space-time warping of space that relates to that theory. As an example, according to the gravitational theory and general relativity, objects that are closer to, if you have a watch or a timer that's closer to an object that has a lot of mass, like Earth, time gets much slower as opposed to farther away. And they use that in the movie Interstellar. Anyone see it? Okay, if you see the movie Interstellar, there's a scene where 2 of the astronauts go to a planet that has a lot of mass. They leave 1 astronaut behind. They're only on the planet for about an hour, but when they get back, the other astronaut is 50 years older. So when you're closer to an object with mass, which they went to the planet, time slowed down a lot. And we experienced that our satellites and the clocks on Earth, the clocks on Earth run slower than the ones that are on the space station. So again, they have to account for that. Recommended reading. I have a list for you. This book, I came up with the speech title, and then I found this book. So it's actually really good. I got it out of the library. He goes into a lot more examples. He throws in some math. What's nice is he puts the complicated math in the back, so you can just do the simple math and skip all the complicated stuff. The first one, Einstein, Relatively Simple. This is George Gamo's Mr. Tompkins in paperback. It's interesting. If you don't I would read this one first and then maybe look at this one, because this one, he doesn't fully explain it. He just says, it's going to be contracted. He doesn't really go into the details, but again, interesting. Cosmos, which came out about 5 years ago, was a TV series. There's an older one from the 1970s with Carl Sagan. This is with Neil deGrasse Tyson. He has, I think even the first TV one was about this idea. Hawking passed away this year. He has some really great books, and I would really recommend what they say is the next Hawking, Carlo Rovelli. The Order of Time, which I have here from my Columbus Public Library, was excellent. He basically says whatever you think about time is wrong, and he uses a whole bunch of theories, including this, to say what you think about time is not the way it is. I hope you got even a little bit or something out of this.
Thank you.
And have a good rest of the day.
I'm just going to